So now let us analyze the diode circuit. Okay, let's take an example and analyze the diode circuit. Okay, so that we'll get a clarity. So say that I have a diode. And then I have a DC voltage of say 5.7 volt, and then I have a sinusoidal input of 1 millivolt sine omega t. Okay, and then so I have a resistor R is equal to 5 kilo ohm, let's say, and as usual this is ID and this is VD. Okay, now what is my ID and VD? How do we calculate for this situation? So first things first, you try to find out the DC operating point. That is very important. Okay, so for finding the DC operating point, if you have any signal in the circuit, you just disable the signal. Meaning, if you have a voltage, if you have a voltage signal here, I've actually shown this as a voltage signal, then you can just remove it. Meaning, you short the signal, you short this particular scenario. So you just represent this circuit for large signal analysis or DC analysis, DC or large signal analysis. Okay, what do? The circuit will change like 5.7 volt and the signal will be shorted, and you have a resistor of 5K and you have a diode VD and current as ID. Okay, this is what it is. Let's call it VDC and IDC. Let VD and ID be the final values. Okay, with addition of this increments also. So what do we have? So we of course it's straightforward because it's 5.7 volt and some will be dropped here and the rest will appear here, and this voltage is connected to the ground. So of course this diode is in forward bias. So when diode is in forward bias, you can assume this particular voltage that is dropped across the diode to be approximately equal to 0.7 volt. Okay, so if this voltage is 0.7 volt, then this voltage anyway is 5.7 volt, then this current flowing in this direction is the current flowing here also by KCL. So 5.7 minus 0.7 divided by 5 kilo ohm is equal to my ID, which is equal to 1 milliamp, right? So my ID is now estimated, it is 1 milliamps, right? So what is VD or IDC? Rather, this is IDC, and VDC is approximately equal to 0.7 volt. So this process of estimating the DC voltage and DC current is very important. Okay, this DC voltage and DC current, in this case it is 0.7 volt and 1 milliamps, is called the Q points or quiescent points. Okay, it's called the Q point or the quiescent point. Okay, now coming back to the main circuit. Okay, how do you calculate the total response? We have calculated only the DC response. Now we know that I will convert the diode in the incremental picture. Now this is DC or large signal analysis. Next analysis is incremental analysis. So now what I will do, I will convert every non-linear element in the circuit with its incremental equivalent, and it is going to be a resistor, right? And it will be straightforward for me to solve, because in incremental analysis every single element that you draw in the circuit is going to be linear, and you are well versed in linear circuit analysis. That is what we have done the whole of the last semester, right? So we know how to solve linear circuits, we know lot of methods to solve linear circuits. So that is what we will be doing. So first of all, let's go from this side. So here you have disabled the signal for DC. Here you cannot disable the signal, so the signal will appear as such, okay. And then what about the voltage source? Incremental equivalent of the voltage source is a short circuit. That is what we have seen last time, right? So incremental equivalent of the voltage source, DC voltage source, is a short circuit, and incremental equivalent of a resistor is a resistor itself, because a resistor itself is a linear element. You take derivative of the resistor, I mean, like, you know, V is equal to I into R. You take derivative of V by I, it is going to be R itself, right? So because you know, it is a linear element, and incrementally the linear element will still remain as a linear element, okay. And the diode, we know it is going to be a resistor again, and the value of the resistor is VTH by ID, okay. So this particular voltage source is 1 millivolt sine omega t, okay, and this is the delta I, and this voltage is delta V, okay. So it is now straightforward. So 1 millivolt sine omega t, rather delta V, is equal to 1 millivolt sine omega t into VTH by ID divided by VTH by ID plus R, okay. So voltage divider rule. And once you obtain this value, then 1 millivolt sine omega t minus delta V, okay, divided by R is going to be delta I. Simple. Done. So this is what is the incremental analysis, or incremental voltage and incremental current. So the total voltage and total current, or ID, will be equal to IDC plus delta I, and VD is equal to VDC plus delta V, okay. This is the total response.